Hello everyone, Simon here. I promised I would go through the week 10 in-class task questions with a nice pen on paper view so you can sort of get an idea of how you're supposed to approach these questions and how you should take a look and what you should write and how you should get out at a good answer. So yeah, let's get into it. So for lab 7, combined sorted, the task was to take two sorted lists and turn them into a new sorted lists, removing any duplicates along the way. So we were given that a node had some int data in it and it had a pointer to the next node. So pretty standard linked list stuff, something like this, int and then next, and the int is called data. So in general, the approach for combining two linked lists into a new linked list, I'm imagining you would draw something like this with a few numbers, and let's do I don't know, 1, 3, 5, and down here we'll do 2, 3, and I don't know, 6, and maybe 7 and 9. And each of these would be connected like this. So the efficient way that I imagine doing this type of thing, and if you've done data structures and algorithms, you should be very, very familiar with this, is that you take, you look at the two smallest nodes, these are in order, so these are the two smallest nodes, one of them must be the smallest overall. You look at these two and you say which one's smallest, and then you take that one and move it over. So you take this one, move it over here, and then you get rid of it up here, right? And then you look at these two and you say which one's smaller. Okay, it's 2. So you take 2, put 2 over here, this one's been gotten rid of, get rid of 2 here, and then you look at these two and say which one's the smallest. Now the trick here was we were asked to remove duplicates. So in this case, we want to look at this 3, and be like, okay, let's grab one of them. I'm just going to choose to grab the top one, get rid of that, and then we want to get rid of this one as well, so we don't have any duplicates. And then we're looking at these two. Okay, and we just kind of want to repeat that pattern going through. Just imagine you got 2 fingers, and you just flick back the smallest one, and whenever they're equivalent, you just get rid of them. Okay, so our question then is, let's think about this. Where is it? We are guaranteed the list is sorted in ascending order, empty list count is sorted, and we need to implement the following function. So it specifically tells us we're going to return a struct node star. It's going to be called merge underscore sorted, and it's going to be struct node star left underscore head, and then struct node star right underscore head. So you get a left list and a right list, which is nice. Now I think a lot of people, maybe they do a bit of thinking like this, planning out their algorithm, they have a little vague thought. A lot of people seem to see this code and then immediately jump into some squiggly brackets and just start putting stuff in at the first attempt. What I would recommend is sort of breaking down the steps of what you're going to do first in a rough idea, which I saw some people did. They tried to write some pseudocode. What I would do, rather than just write pseudocode, because that's kind of the same, rather than just writing out everything you're going to happen in C, you're just kind of writing it out in English. I would approach how you feel it should go and identify the common components of that. So the components that I mostly notice is this act of taking a node up here and moving it down to a new list, right? So obviously you're going to have some pointer. Actually, let me draw a little fresh picture here. Plonk, 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 plonk. So you're going to have some kind of cursor, right? Keeping track of where you are in each list. So I'm going to put this like here and here. And every time, say I want to fetch this node and add it to my new list, I'm going to have another cursor pointing to the beginning of my new list, and a 4th cursor pointing to the end of my new list, so I know where to add my new nodes. So what I seem to want to do is take this, right, I want to set this thing to point to this, and I want to set this to point here. So what I'm noticing is that I want to advance this one to the next part, and I want to move this down. I think a convenient way to do that would be to make that a function. So I'm going to have a function, I'm thinking, which takes in a cursor. Cursor goes into my function, and it moves cursor forward, moves forward, and returns head. Returns head. Right? So this cursor is obviously going to have to be a double star, because this cursor is itself a star to a node, and I'm going to have to adjust the value of this. So I might call this function, if you've seen my solution already, you'll know that I have called this function advance and return. And that's the first function that I'm going to make. I'm going to take in a cursor, I'm going to advance the cursor to the next node. So I'm going to take this, point it there, and then I'm going to, whatever node it was pointing at, I'm going to return that back to wherever I need to put it. Okay? And then the only other case I need to have is when I have an identical one, I need some way to advance the cursor and get rid of the current one rather than return it. You can think of that as maybe you do an advance and return and then you free the thing that you get returned. I'm just going to make a new function, which again, if you see my solution, you'll be familiar with, called advance and free. Okay, so let's flip over to a new page, and we'll put together exactly how these functions are going to work. So my advance and return is going to return a node. It's going to return the head of the list that we're advancing. So it's going to return struct node star, because that's how we think of nodes as stars. A bit blurry. I'll call it, I'll be brief for advance and ret. I'll be brief for the sake of handwriting, advance and ret. And I need to take in the current list, the list that I want to advance and return. But obviously, if I want to move the cursor forward, I need to be able to access it. I need to pass by reference. So I want to change the value of a node pointer, right? I have a pointer here, which points to a node. I want to access this node, sure. But I also want to access this pointer, and I'm within a little function box. So I need a pointer to the pointer to move the pointer forward, if that's unclear. So I will call this cursor. And this function is very bite-sized. It's very simple, which is a good sign for style. So I'll look at this function and be like, okay, I need to advance my cursor and return the node it has. So let's first off make a struct node star temp, which is going to store what the node is, the current node is. So it's going to be the value at cursor, of course, right? And now we immediately have an edge case. I'm assuming cursor itself isn't null, but what if it's pointing to a null node? What if there's nothing left in this list? Well, thinking back to my original problem, if one of my lists is empty, I don't really want to raise any errors. I just want to advance nothing. There's nothing left to advance. I just want to get the right list. So if I have no temp, I just want to return immediately without having done anything. Okay? But if I do have a temp, if temp is not equal to null, I'm going to want to return, let's say, I'm going to want to set the value at cursor to be equal to temp next. So I'm going to update my cursor so it points to the next value. Seems fair enough. Oh, this should be a squiggly bracket. Sorry, it's a little late. Okay, and then after that, I just want to return temp. And this actually covers our edge case quite nicely. So if we are given a cursor to nothing, given a cursor to null, right, we will say, oh, well, temp is now null, so we won't do this thing, and then we'll just return null. So we're going to say, oh, you're giving us an empty list, well, there's nothing to return, so we'll return nothing. That seems very natural to me. And then, of course, advance and free is going to be very similar. Struct node star, advance, and free, which also takes a struct node star star cursor. Again, I'm going to assume that cursor is not empty because you have to give it a valid cursor, but cursor could be pointing to something that's empty. It could be pointing to a null, an empty list. Yes. So, advanced and free. I want to do this same advanced step, but instead of returning to, this doesn't need to return anything. This is a void. Instead of returning temp, I'm just going to free temp. So we'll just do struct node star temp equals value at cursor, and then if temp is non-null, not equal to null, then I want to do cursor equals temp next. I want to do my advance, and of course if temp is not null, then I want a free temp, which seems reasonable. And I'll close that, and I don't need a return value because it's a void function. Excellent. So now I have the ability to, when I have my two lists like this, I've got some cursor pointing to them. If I want to get the first one to move the cursor along, I advance and return on that cursor. And the way I have to find it, if this is pointing to nothing, it just gives me nothing, and I don't have to worry about it. If I do advance and free, it's the same deal. I give it a cursor, and it'll just free what's there and move it along. If there's nothing there, it just gives me nothing back. Well, it gives me nothing back anyway, so I can keep calling null on it as much as I like, and there's no issue. Keep calling it on null, sorry. Okay, so now I've got these two functions, right? We need to consider like our main flow loop. Okay, so as I said before, we're going to have 4 cursors in total. We're going to have to keep track of the head of our new list, so new underscore head. We're going to have to keep track of the tail of our new list, so I'll call that this one. This is new underscore tail, because we need to know where to append our new nodes, and we're going to return the head. And then we need to keep track of our left head and our right head. So I'll just call it left, points here, right, points here. Okay, so I have the ability to grab the node. So the general loop I'm doing is while my new tail is, say, non-null, while I can keep adding nodes, I just want to grab the smallest of these two, if it exists, unless one of them's empty, then I'll just grab whichever other one, and I want to advance and return it back in, unless they're equal, in which case I want a free one, return the other. Okay, so I want to make this another function, this smallness logic function, called struct node star. I'm going to return struct node star, I'm going to call it smallest, and I'm going to give it 2 lists. Again, because this function is going to call advance and return, these have to be double pointers, pass by reference. We node star left, and it's going to be struct node star star right. Okay, so let me open this up. I'll make some squiggly brackets. So of course I'm going to want to mostly going to want to deal with the left and right values. So what I want this function to do is return the smallest of the 2 of these, having advanced and moved along and handled any nice edge cases. It's going to return the smallest value so I can append in a nice loop. So this is going to get me the node that I want to append. Okay, so if both of them are null, that seems like a pretty trivial edge case. If the left has reached the end, null, and the value at right is reached the end, null, I'll just return null. There's nothing to do. Return null. Okay, so if both my lists are empty, then there's nothing to do. Easy. If one of my lists is empty, say the left list is empty, right? So if value at left is empty, then I want to advance and return the right, because we know that there must be something in the right because this check didn't pass, so we got down here. So I'll just return advance, return right. And remember, this takes a double pointer, so you don't need a star here. You can just do right. And likewise for if value right is null. Value right equals null. I had to spell Simon. Null, blah, blah, blah. I'm going to return, advance, and return. Just return the other one. Seems pretty straightforward. So if one of the lists is empty, just keep returning the other one. Okay. And then we get to the interesting part. So we now know both lists are non-empty, so we can start comparing things. So if the value at left, first node of left, if its data is less than the first value on the right list's data, that means left is our smallest one, right? So we're looking at our two nodes here that at the beginning of our list. If this one has, let's say, the number 1 and this one's 2, this one's smaller. So we're going to want to advance and return the smaller one. So you just do return, advance, and return left once again. Right? And the advance and return, you can see here, it's really doing a lot of the heavy lifting for us, which is quite nice. Okay, and I can sort of do something similar for right. So I'll just do like left data is greater than right data. This gets a little repetitive as you get through things. Return, advance, and return the right list. Yes, if right is small. Now we get to our edge case. If they both happen to be equal, right, down the bottom here. So one wasn't less. So first off, both of them weren't null. Left wasn't null. Right wasn't null. Left wasn't smaller. Left wasn't bigger. That means they must be the same. So in that case, we want to advance and free one of them. It doesn't really matter which, but I'll say the right one. And then we'll advance, and then we'll return, advance and return left. So when they're equal, right? So in this case, we're thinking like we've got 2, 2, right? If both of the beginnings of the lists are equal, we want to just get rid of one of them because we don't want any immediate duplicates. And then we want to return the other one. So we get rid of the right one just because, and then we return the left one. And then that's it. That's our smallest function. So this really handles this function. The idea is every time you want to compare two nodes, it's one step. You just do this. Okay? And of course, I've been a bit clever and a bit like nice and organized about how I put this together and told you about it, so it's very clear. So that our final function, merge sorted, ends up being very nice. So now we want to look at struct node star merge underscore sorted. Okay, so this takes no star, yeah, left, and right. You know what I mean. Okay, so struct node star, blah 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 star, right, and we're going to need to keep track of the left head. So as I said before, we're going to need 4 cursors, which is great. So there's left underscore head equals left. There's right underscore head equals right. And these are all going to be struct node stars. There's new underscore head, and there's new underscore tail. Okay, so new head, I might just immediately say this is the smallest of left underscore head and right underscore head. Remember that smallest might update the values of my left and right cursor. So I need to pass by reference. I need to pass in the address of the pointers. Should be a common idiom for you here. It's like every time this might change that, you got to pass by reference. And then new tail is going to be new underscore head to start with, because there's only going to be one node in the beginning. And then we basically want to go until our tail is empty. So until new tail, so while new tail is not equal to null, right? We want to advance, which means we want to say, let me think of this. New underscore tail. We want to append the next smallest onto the list. So new tail new tail next. We're going to set equal to the smallest between address of left, address of right. This should be underscore head there. And then we just want to say new tail equals new underscore tail next. So the idea here is that basically that is the function, and then we just return new underscore head, which gives us a nice just barely 20 minutes. It's a bit late, so I'm kind of talking a bit slow. But the process of this, right, is that we sit here looking at our new head. To make our first new head, we do our smallest, which grabs our smallest, we put it here. Cool. And then we've advanced our left list. Straight away, let's just step up here. New head is new smallest. We set new tail to new head for now. And then until this becomes null, until new tail is pointing to nowhere, we grab the smallest and add it onto the end. We say the next node from new tail is going to be the smallest between left and right. Cool. So we grab the next node, and then we set this to point to the next node. And then we keep going. So we're really going through the motion of grab the left, grab the smallest, move it in. Grab the smallest, move it in. Grab the smallest, move it in. And of course, our smallest one nicely handles edge cases where we get nulls. So if one of these lists run out, smallest would be like, oh, it's null, so I'll just immediately grab from the right one. That's why we did those nice edge cases before when we looked at smallest here. That's why we're checking these. So if at any point we have a null list, right, we just return the other list. If both of them are null, then there's nothing less to keep flicking back, so we flick back nothing. And at that point, new tail next is set to null, because that's what we flick back. There's nothing left to flick back. So new tail equals null, so this fails, and then we return new head, which I think is quite nice. So I would say, I'll admit that this problem ended up being a bit longer than I had intended in my head, and I'm sorry about that. I did do my best to go a bit easy on the marking to make sure that everyone had a reasonable chance. But I do think it is a good problem to ponder and think about, especially in terms of just, applying lots of data structures knowledge, which is really essential. And also a good practice for the exam. So my general advice for these problems, especially when you're doing them in exam and exam practice, is to make sure that you make it really clear what your code is going to do. So first off, think. And I don't just mean sit and ponder for 2 minutes and then start writing code. I mean sit and really be like, okay, this is going to go here, this is going to go here, this is going to go here. I know that's really difficult to do in an exam, and it's very stressful to think, oh, how am I going to, sit and do this here, I've got so much to write and things. But get some practice at it now, and you'll be okay. Think about exactly what it's going to do. And then once you've thought it through, after you're pretty clear on it, translate it, okay? Now, I obviously am a pretty experienced C programmer, so I was very quick at translating and immediately knowing where I needed to put references in. But if you're making a function like advance and return, it's going to take in a node, like struct node star, left or cursor or whatever. And then you might suddenly get to the point, like if you're writing it, you might think, oh, struct node star, blah, 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 cursor, right? And this is going to be like a star. And then you might suddenly realize you need to update the cursor where it originally is. You suddenly realize, oh, I want to go cursor. That's not actually too bad. You just add an extra star. Every time you've referred to cursor, you put brackets cursor around it before. And then you can do things like just cursor equals whatever, right? It's very easy to retroactively add in a pass by reference if you need to. I kind of did that right off the bat. I was adding my double stars, and I know that can be confusing. But if you're not sure, start with a single star as you normally do, and then when you realize you need to change something, add in the second star, add in dereference operators, and add in an ampersand when you call the function. And then, once you've done that, once you've thought and you've translated, right, 3, I would, if you have time, just double check it. That's the general process here. And while you're thinking, I would suggest think about individual steps, very individual, and then put that into individual functions. That's really the key idea here. Okay, so that has been the Lab 7 combined sorted week 10 in-class task. Again, I apologize that it was actually quite a lot of code. I ended up writing 4 functions, which is quite a few, especially in a 20-minute time. But yes, I would highly recommend for the sake of practice, going through, say, Lab 5 was my other class, so I'd recommend doing that question under a 20-minute timer, taking a deep breath, giving it a go, and then also you can look through the video tutorial of that one, because I recorded one of those too. And yeah, I hope assignment 3 is going or has gone well, depending on when you find this video, and good luck for your exams. Thanks.